In the videos on linear stability analysis, we studied linear systems. The crib sheet of linear stability analysis can also provide partial information when investigating systems that are not quite linear. In this video, we will study an example of a topology that exhibits adaptation. The topology is described in a paper by authors Ma, Trusina, El-Samad, Lim, and Tang, published in the journal Cell in 2009. Adaptation is a system's ability eventually to restore a variable to a previous steady-state level even though an input that triggered a temporary change in the variable persists. If the steady-state value is identical before and after the jump, the adaptation is perfect. In this video, we will study a particular example of the incoherent feed-forward loop, study its phase portraits, and study its dynamics. In the next video, we will review the strategy of analysis used in this video. We are inside a cell. The number of copies of enzyme A is the input. Enzyme A is a signaling factor whose abundance is prescribed by the so-called outside environment. In this toy model, the cell cannot modulate A, only respond or not to it. Enzyme A catalyzes the conversion of B' to protein B with rate coefficient beta. Protein B degrades with rate coefficient alpha. The time derivative of the amount of B is owing in part to catalysis and owing in part to degradation. The partial change in B owing to a catalysis event is a gain of one copy of protein B. The law of mass action guides us to write down one factor for each reactant B' and A. The partial change in B owing to a degradation event is a loss of one copy of protein B. The law of mass action tells us to write down a power of B. Green protein E has a binding site that fits molecule C'. If protein E can bump into molecule C' and at the same time bump into protein A, the entire collision can generate protein C. This reaction occurs with rate coefficient gamma. If unbound green enzyme crashes into protein C in an unlucky way, it can become bound, leaving the population of free green protein EF and joining the population of bound green proteins EB. Occasionally, the protein C shakes itself out of the binding wedge of the green protein, so there is binding and unbinding. If there is a lot of protein C in the cell, a lot of the green protein might be bound away, making it unavailable to catalyze the conversion of C' to C. Suppose that the degradation of C involves collision with B and a rate coefficient delta. The time rate of change of C is owing in part to catalysis events and owing in part to degradation events. The partial change in C owing to a catalysis event is +1. Applying the law of mass action to the reactants in the three-way collision permitting catalysis gives us one factor of the unbound green enzyme population EF, a factor of the population of A, and a factor of the population of C'. The partial change in C owing to a degradation event is a -1. The law of mass action here prescribes a power of B and a power of C. The population of C can change when it is titrated away by the green enzyme. We neglect this effect for the purposes of this model. The unbound green protein population is the unbound fraction of the total green enzyme population. The video on Hill functions helps us to express the bound fraction for the illustrated binding and unbinding reactions with a Hill coefficient of 1 and a critical concentration parameter here called C-half. Doing some algebra shows that the unbound fraction also looks like a Hill function, but with the parameter appearing upstairs and downstairs, and with the variable concentration appearing once downstairs. Substitute EF back into the equation for the time derivative of C. In this video, we have two purposes. We want to describe adaptation. We also want to demonstrate the application of eigenvector-eigenvalue analysis to a system that could not directly be written as a matrix equation with constant matrix elements. The molecular circuit on this slide has been contrived to serve both of these purposes. The differential equations describe the dynamics of the levels of B and C in the context of an externally maintained level of A in terms of some parameter coefficients. Dirty trick. If you don't know what parameter ranges are realistic, you should see what happens when a parameter vanishes, when it's much smaller than 1, when it's closer to unity, and when it's much greater than 1. You adjust the parameters individually to explore the behavior of the system for different combinations. For example, when one parameter is much greater than unity, while another is much less than unity. For this exercise, let's look at a situation in which we make all the parameters close to 1. If we set the orange and blue parameters here equal to 1, dB dt equals a minus b. Let's try setting the green, yellow, and pink parameters down here equal to 1, 1, and 1/2. We're using a 1/2 instead of 1 for the pink parameter because otherwise a lot of the subsequent calculations will have all sorts of messy square roots floating around. The time derivative of c is then a over c plus 1 minus bc over 2. Let's clean up the visual representation of the interaction between protein B and C. The more protein B we have in the cell, the more often it can collide with protein C to cause protein C's degradation. Protein B helps to get rid of protein C. In this sense, protein B inhibits C. To clean up the diagram further, pay attention to the bold flowchart arrows and suppress the faint blue ones. The input A directly activates the output C, but also indirectly inhibits C by activating its inhibitor B. The two arms of this diagram seem to fight. This is called an incoherent feed-forward loop. We can use the flowchart to give a word model description of adaptation in this kind of circuit. A sudden increase in input A temporarily increases the level of protein C, but after the increase in input A works its way to increase the level of the inhibitor B, the level of C can be brought back down to its previous steady-state value. This topology is one way to get adaptation in a system with 3 molecular entities A, B, and C, or so to speak 3 nodes. To add quantitative understanding to our word model, let's look at the nullcline for B. It's the curve defined by the relationship B equals A. For example, if the external input is held at A equals 1/2, the nullcline for B in the BC phase plane is a vertical line at B equals 1/2. We also consider the nullcline for C. Move stuff to the right. Do some multiplication and rearranging to get a quadratic equation whose solution is C equals 1/2 the quantity minus 1 plus square root of 1 plus 8a over b. You may pause the video to consider why we have disregarded the other root with a negative sign in front of the square root. As the factor b in the denominator increases, it makes the fraction 8a over b smaller, which makes the entire square root thing smaller, making c smaller. For larger and larger values of b, the value of c gets smaller and smaller. If b is large enough that we can pretend that the stuff in the square root is just 1, then c equals 0. If b becomes tiny and tinier, the denominator in the factor 8a over b becomes very small, making the term 8a over b gigantic. If b becomes arbitrarily small, the square root thing, and thus c, can become arbitrarily large. Together, these considerations trace out a nullcline for C that approaches a vertical asymptote to the left at b equals 0 and a horizontal asymptote to the right at c equals 0. The critical point is the intersection of the nullclines at coordinates bc equals a and cc equals that thing with bc explicitly substituted. But we just said that bc equals a. The 9 in the square root is really a 3, which when you take away 1 and then divide by 2 gives 1. The critical point is always at the height cc equals 1, regardless of the value at which we hold the external input a. Consider a different problem where a is held equal to 1. The nullcline for b pulls to the right. In the equation for the nullcline for C, an increase in A corresponds to an increase in C, so the nullcline for C is vertically elevated relative to the previous plot. The critical point is at the same height, CC equals 1, when input A is maintained at unity as when input A is maintained at 1/2. Think about the increase in input A from 1/2 to 1 in the following way. Starting with A equals 1/2, a change to A equals 1 is an increase in A that increases the catalytic generation of protein C. In the equation for the dynamics of C, this corresponds to a momentary increase of the positive term, so that the positive production term and negative degradation term no longer cancel out as they previously did. If B were constant, the level of C would increase so as to crank up the negative degradation term relative to the positive production term until the system approached a new position in the phase plane where the positive and negative terms canceled out. However, B is not constant. Increasing A increases the level of B and the inhibition on C. An increase in A increases the time rate of production of B, which can now be sustained at a higher steady-state level. Notice that the increase in B is like increasing a rate coefficient in front of C in the negative degradation term of the differential equation for C, so the system cannot sustain as high a level of C as we thought when we marked the dark orange circle outlined in gold. Instead, the critical point sustains a lower amount of C, and that corresponds to downward displacement. This is a result of the increase in the steady-state value of B depicted by the horizontal displacement to the right. The direct activation of C owing to A is compensated for by an indirect inhibition through the action of B so that, overall, the steady-state level of C neither rises nor falls but instead equals its previous value. The steady-state level of C before and after a change in A is the same owing to compensatory changes in the effects of A and B on C. In the last section, we used Nullclines and critical points to understand that the steady-state level of protein C was unchanged after a shift in external input level A because of a compensatory shift in the steady-state level of protein B. In the next section, we use something that looks like the eigenvector-eigenvalue analysis that provided the general solution of the gene transcription-translation model to study the time courses of the levels of protein B and protein C as the cell encounters a sudden jump in the level of the external input A. We will look at how the system responds to a sudden increase in the level of A from the level A equals 1/2 maintained into the eternal past to the level A equals 1 maintained into the eternal future. On the phase plane, write out a new coordinate system centered on a critical point. Since the critical point moves horizontally depending on the value of the external input A, we actually have a new coordinate system for each value of A. This one is drawn attached to the orange critical point corresponding to A equals 1. We define delta B as a horizontal displacement from the critical point and define delta C as a vertical displacement above. Before or after the jump in A, the variables delta B and B differ merely by a constant A, so these time derivatives are equal. Substitute from above for dB dt and compare with the definition for delta B to express the time derivative of delta B as the negative of delta B. Delta C and C differ by a constant, so their time derivatives are equal. Use the definitions for delta B and delta C to express the time derivative of C in terms of delta B and delta C. It doesn't look very nice. Let's denote by the letter G all of this gobbledygook, a function of delta B and delta C. Assuming we didn't make algebra boo-boos, the value of G when delta B and delta C equals 0 should itself be 0 because the time derivative of C and its proxy delta C are 0 when the system has precisely no displacement from steady state. For small displacements from the critical point, let's focus on the first terms in a two-dimensional Taylor expansion for G expanded around the critical point. The partial change in G owing directly to a change in delta B is found by differentiating G with respect to delta B, pretending that delta C is a constant. The stuff attached to the lone power of delta B is -1/2 times the quantity delta C plus 1. Evaluating at the critical point where delta C equals 0, we obtain the slope -1/2. The partial change in G owing directly to a change in delta C is the derivative of G with respect to delta C pretending delta B is constant. There's a quotient rule floating around in the first term. Evaluated at the critical point where both delta B and delta C equals 0, this slope is -3/4 A. Taken together, the first terms of the Taylor expansion for G, meaning the time derivative of delta C, look like this. Ignoring squared and higher-order terms allows us to express the system in terms of a matrix equation. Solve for the eigenvalues of this approximate equation by attaching minus lambdas to the main diagonal elements and forming the product of the off-diagonal elements. In this case, you can read the eigenvalues off directly as lambda 1 equals minus 1 and lambda 2 equals minus 3/4 a. You can verify that these eigenvectors correspond to these eigenvalues. If a equals its initial value of 1/2, the critical point is the orange pebble to the left, and the components of the orange eigenvector are 1 and 4/5. This corresponds to the orange eigendirection whose vertical component is almost, but not quite as big as its horizontal component. If you look closely, the orange arrows are slightly shallow compared to arrows pointing at 45 degrees with respect to the horizontal axis. Regardless of the value of a, meaning both before and after the level of a jumps, the blue eigenvector has components 0, 1, meaning it's vertical. While the blue eigenvector points in the same direction regardless of the level of a, the corresponding blue eigenvalue varies with a. When a is initially 1/2, the blue eigenvalue is minus 3/8. The orange eigenvalue is minus 1, which is more negative than the blue eigenvalue minus 3/8. The orange eigendirection is fast, the blue eigendirection is slow, and so we sketch trajectories starting out kind of parallel to the fast orange eigendirection and then transitioning over to eventually approach along the slow blue eigendirection. The steady state is asymptotically stable because the eigenvalues are both negative. What happens after the level of a increases? If a equals 1, then we are interested in the critical point to the right. The orange eigenvector has components 1, 2. The vertical component is twice the horizontal component, so the orange eigendirection is now steep. The blue eigenvector still points in the same direction, but the blue eigenvalue is now minus 3/4 instead of minus 3/8. The orange eigenvalue minus 1 is still more negative than the blue eigenvalue minus 3/4, but now the eigenvalues are more comparable, so when we sketch qualitative trajectories, we can draw a pattern a little more like the star situations that can occur in systems with equal eigenvalues. The trajectories look more like straight lines compared to the dashed trajectories in the background. We've softened the bends in the curves. Let's put together the linear stability analysis we performed on the two critical points. When a initially equals 1/2, it provides some activation to protein B, corresponding to sustaining B at the value indicated by the blue nullcline. A also directly activates C, sustaining some sort of level of C. The nullcline for C decreases with increasing B, owing to the inhibitory effect of B on C. The critical point when a equals 1/2 is here. Eigenvector-eigenvalue analysis on the first pieces of a Taylor expansion of the differential equation system, or a so-called linearized system, indicates that we have a stable node. When a is later equal to 1, its contribution to the production of B increases, so the system can sustain a higher level of B moved to the right. But the increase in A also contributes to an increase in the amount of direct activation of C, lifting the red nullcline, meaning allowing the system to sustain elevated levels of C at given values of B, and thus moving the critical point horizontally to the right. Eigenvector-eigenvalue analysis on the linearized system helps us plot examples of trajectories approaching the second critical point, including this one, which passes through the initial critical point corresponding to the initial value of a equals 1/2. Let's plot the dynamics of proteins A, B, and C as functions of time. Before time t equals 0, we maintain the input A at 1/2. We've been maintaining A at 1/2 since time immemorial, so let's say that the level of B has long since settled to near the steady-state value corresponding to this value of A. At time t equals 0, the level of input A in the cell discontinuously jumps to a new constant value 1. The level of protein B can eventually approach its new steady-state value, but it does not do so instantaneously. The gradual upward motion of B from below toward its new steady-state value in the plot versus time on the roller blackboard corresponds to horizontal motion to the right in the yellow curve in the phase portrait. The steady-state value of C established by the compensatory effects on C of direct activation by B and indirect activation by A through B corresponds to this pink horizontal line segment. Again, we presume for simplicity that A has been maintained at A equals 1/2 for a sufficiently long duration that C has long since become very close to this steady state, even if it held a different value at some time in the distant past. We know that the steady-state value of C is unchanged after the jump in A, so we expect that the level of C will eventually approach the same value it hugged before the jump in A. However, in the interim, the level of B has not yet risen to the level needed to provide compensatory inhibition for the recently increased direct activation by A. The temporary partial inability of inhibition from B to compensate for direct activation allows the level of C to show a transient increase. The transient bump in the plot of the level of C versus time on the chalkboard corresponds to the vertical rise and then descent of the yellow curve in the phase portrait. Eventually, the higher levels of B at later times help bring the level of C back down toward its original steady-state value. In this video, we described adaptation in a word model. Then we used Nullclines and critical points. Finally, we used a Taylor expansion and eigenvector-eigenvalue analysis to describe the dynamics of the system. This system displays adaptation. By slowly resetting the level of C after a jump in the input, the system can reuse a narrow range of values of C to describe a sequence of step jumps in A.